the phone number or?
Either one. Either one.
Okay.
You can share the phone number, or you can.
Okay.
How's it going, everyone? All right. I'm looking at our calendar and I'm just like, I'm depressed. I'm so depressed right now. This is where we're supposed to be. This is where we are. So, ay. We'll try and make up some ground. I think we can make up some ground right here. These two sections right here are a review from College Algebra. So in College Algebra, you studied exponential functions, you studied logarithms. And so usually I can do all three of these in one day, because I can spend very little time reviewing those two. So I might have you before those classes we get to them, I might have you go just review a couple of videos, just so you're not sitting there going, oh, I don't remember what an exponential function is, you know, and we can move through it a lot faster. So, okay, let's get down to business. Chain rule. We started talking about chain rule last time, but I never gave you like the formal formula for it or any like, I never like gave you anything other than just anecdotal stuff to think about. So today I'd like to give you the chain rule formally and work a lot of examples and give you some examples to work, because this is really going to be like the make or break idea for you. All right, chain rule. So let's get down to business.
Awesome.
This says, go ahead. What? You're good?
Yep, I was just.
Okay. All right. So there are a few things we have to know going in, and that is, you know, what is functional composition? What does it mean when you compose two functions together? It's different from multiplication. It's different from division, right? It's different from addition and subtraction. Composition is when you take one function and you plug it into another function, and that operation is unique to functions. In other words, when you're learning about numbers, right, like back in grade school, you're taught of the four operations between numbers, right? You can add them, subtract them, multiply, and divide. So you have these four operations that you do with numbers that you can also do with functions, right? You can take two functions and add them. You can take two functions and subtract them. You can multiply and divide. But there's this fifth thing that you can only do with functions, not with numbers, and that is composition. So because of that, we have to know how to take the derivative of two functions that have been composed together. And that's what the chain rule is. It gives you a formula of how to do it. So let's just look at this formula. It says, suppose that y is equal to f with g plugged in. Now in college algebra, you may recognize that as being this notation, f, o with a little o between them. And we say that f of g of x. And your algebra teacher might have said fog. I don't know, maybe fog x or something like that. I never say that, but you know, that's, if you have heard it, you know, I understand you've heard it. This right here, this notation really just means this. It means you take the g function and you plug it into f. So visually what's happening here is we're starting with some value x. That x first is going through some function g, coming out as g of x. And then that entire expression is going through another function f. And when it comes out as the value of f at g. So let's look at one specific example of a composition. Let's say we have y equals sine of, let's go x squared plus 1. If we look at this example, we can identify which function is the f function, which function is the g function. So the f function, well, let's start with the g, the inside. The inside function, right, the inner one, that one is going to be our g of x. And so we could write here g of x is equal to x squared plus 1. And then the f function is the outer function. This is our f of x. So for us in this example, f of x would be the sine function, sine of x. So if you take g, take that and plug that g in right there, then you would have the original y up here, y equals sine of x squared plus 1. Does that all look familiar from college algebra? That kind of idea? Yeah. Okay. So the question becomes, if we graph this function, right, what is the slope of the tangent line, right? What's the slope of the tangent line? And the answer is this, okay? This is our chain rule right here. So what the chain rule says is that what you're going to do is you're first going to find the derivative of the outer function. Okay, this is the derivative of the outer function. Okay, you're going to find out what that derivative is, but you're going to evaluate it at g of x. That's important. You're going to take the derivative of the function, but you're not going to plug x into it. You're going to plug the whole function g into it. And then after you do that, you are going to multiply, okay? You're going to multiply that by, well, now you just take the derivative of g. Or sorry, the derivative of the inner function, I should say. All right. So there's like 3 different ways to teach chain rule. All right, maybe even 4 different ways to teach chain rule. So I'm going to kind of give you different versions of it, and then hopefully you'll pick the one that makes most sense to you. All right. This is the formula in the book, so this is the one I'm going to use to start with, but then I'm going to show you a few other ways. So let's do this problem. Let's just start from scratch, okay? Let's just start from scratch, and let's take this function y equals sine of x squared. Okay, so the first approach for chain rule is this. I'm going to identify the inner and outer function. So the outer one is f of x, which I'm going to say is the sine function. And then the inner one is the g of x, and that is the x squared plus 1. Okay. Then what I'm going to do is I'm going to take the derivative of each of these. So the derivative of f of x is cosine x. We know that, right? And the derivative of g of x is 2x. So we've started with this inner and outer function. We've created these 2 new functions, f prime and g prime. And now we're going to apply the formula. The formula says that the derivative of y should be the derivative of f, but plug g into it, and then multiply that times the derivative of g. So of these 2 things that we have to figure out, the easier of the 2 is this, because what is g prime of x? I mean,
2x. Yeah.
Right here, it's 2x. That's the easy part. That's just 2x. The harder part, or the more confusing part, is that you have to now look at the derivative of f, which is this, right? But instead of plugging X in, right, instead of plugging X, I want to plug G of X in, right? I want to plug this into this. And G of X is actually this in blue, right? That's what I want to plug in right there. So I'm going to write down cosine, right? Cosine, but instead of X, I'm going to put X squared plus 1. And that's it. That's your derivative. Now, if you have a question, I'm going to work another example. Well, go ahead, Ethan. Were you going to say something?
Well, I was gonna say, so if we're like on a test or final or whatever, so how do we identify when to use the chain rule? Is it when you have something like in parentheses like this?
Well, that's a great question, Ethan. You have to recognize what you're looking at as composition. So that's something you would have to recognize. So like, for example, if I had this, let's say I had sine X, and then I had written over here X squared plus 1, that is not composition, because this is not a function inside of a function. This is actually implied multiplication there, and you would run a product rule on this. You see how what's in the sine function is actually this X. And so we can look at this as like, okay, that's F and this is G, and we're multiplying them. So I'm going to use a product rule. Does that make sense, Ethan? Like you have to recognize.
Yeah, but is it only, are they always going to be attached to a trig,
No.
whatever you call them?
Mhm. Let's do it. I'll give you one exactly right now that's not trig. Let's do something that's not trig. How about this? How about y is equal to x to the 4th plus 3x squared plus 1 raised to the 10th power. So nobody here wants to multiply that out 10 times, right? So if we can see this as composition, then we would be able to use the chain rule. If you can see it as composition. So that means, can you see this as being a function inside of a function? And
yeah,
let's see. We need an outer function and we need an inner function in order to do the composition. And I think I did mention last class that the way I think about inner and outer is if I asked you to plug an X in, what would you do first, right? So like here, if I plugged X in, like let's say I said, plug in 2 for X, you would figure out what all this shit is in here first, right? That's the first thing you would do. Then after you're done with that, you would do something else. You would raise it to the 10th power, right? And raising it to the 10th power is like a separate function. It's like a secondary thing you would do. So the inside would be, the inner function would be the G, right? That would be the x to the 4th plus 3x squared plus 1. And then the outer thing that you do is to take whatever's there and raise it to the 10th. Does that make sense
yes.
to everyone? Does anyone have a question? So if I were to take this and plug it in for X right there, take all of that and plug it in for X, then it would basically be this thing. So now I'm just going to crank out the derivatives. So f prime of X would be, well, what's the derivative of X to the 10th power?
10x to the 9th.
10x to the 9th. Okay, and then I need the derivative of G. Well, that I can do, right? Because that's just 3 separate terms, right? Addition between each one. I can just derivative each one. So 4x cubed plus 6x, and then the derivative of 1 is 0. So I'm done. Now I find my derivative by doing f prime evaluated at G times the derivative of G. So that's our chain rule. I already told you the easier part is this part. So G prime of X for us is just this, right? This right here. So I'm just going to write that down. Now be careful. It's 2 terms, right? It's 4x cubed plus 6x. So I need to put that in parentheses. A lot of times people will forget the parentheses, but you're multiplying all of this, right? So if it's 2 things, you need to multiply the whole thing, right? The whole quantity needs to be multiplied. If it was just one term, you don't need the parentheses, but if it's more than one, you need it. Now the tricky part. What I need to do is I need to take the derivative of f, which is this function, but instead of plugging in x, I'm going to plug in g, right? So this thing gets plugged in right there for that x. So I'm going to write down 10. And then all of that stuff, which is x to the 4th plus 3x squared plus 1. But then don't forget, you got to raise that to the 9th power. That's your derivative. We don't need to do anything. I mean, I hope you don't want to do anything, right? Like no one wants to multiply that out 9 times. You cannot pass a 10 through here, right? You cannot multiply a 10 through here because order of operations says that the 9 power has to happen before the 10. Could you multiply the 10 through here?
You should be able to.
Yeah, you could do that. You don't need to, but you could. You could make that 40x cubed plus 60x, all right? But this right here is the raw derivative. This is the thing we want. Okay, let me, are there any questions? You ready for another one? Here we go. Let me see. Kind of group these together here. Baby steps, baby steps, baby steps. I have a tendency to go too hard, too fast on these things. All right, so y equals sine to the 4th of x. So is this composition? One thing that will help us is if we understand what that notation means. Okay, when we put a little 4 like that, and I should mention also, if you see this way, it means exactly the same thing as this, right? I don't necessarily need the parentheses here. This could be written this way also. So we need to understand that this is actually the sine function raised to the 4th. And now we have a function on the inside, which is the sine, right? And then we have a function on the outside, which is the power, the 4. So let's say we can move a little quicker with this. The outside is the f function. What is our f function here?
X to the 4th.
X to the 4th. And then the inner function, which we'll call g, is the sine x, right? And then we will differentiate both of those. So f prime of x, 4x cubed, and then g prime of x is cosine x. And then we apply the formula again. So we want to evaluate the outer function's derivative at g. And then we want to just multiply that times the derivative of the inner function g prime. Now I'm gonna actually move from left to right this time because I normally don't start with g prime. Let's just now keep in mind that g prime is going to be the easy part, right? So I'm going to do f prime, which is this, but instead of plugging in x, right? Instead of plugging in x, what am I going to plug in?
Sine x.
Right? The g function, right? Sine x is going to go in there. So that should be 4 with sine x in here, right? Cubed. So I just replace that blue with this sine. And then times the g prime, which we know is cosine x. I'm going to go one more line because that's definitely not the way it would look in the back of the book. That's the way it would look in the back of the book, because we normally don't use this notation only when we're actually doing, you know, the actual rule. Once we get it to the derivative, we just, oh, okay, we know that this means this, right? These mean the same thing. So that's it. Okay,
Question.
yes.
On a test, would you want it to be in that last form there?
Like, would I care if you wrote it this way?
Yeah, like,
I would not care. I
because
would not
like,
care.
to be honest, in my head, the 3 being outside of the sin x makes more sense.
Yeah, and it's a terrible notation we have. It's one of there's a few places in math where we have problems with notation, and that's one of them. Because if you write sine squared x, right? We understand that to mean sine x squared. But if you write sine to the negative 1x, then this does not mean sine x to the negative 1. Sine x to the negative 1 would be 1 over sine, right? Which is cosecant. And that's not what this means. This does not mean cosecant. This means the inverse the inverse sine function.
Yeah, that's the arc sine.
Yeah, it's arc sine.
Oh,
And
that
so
makes
that's
sense now.
just, that's just,
Yeah, so that's a screwy one then.
it is. The other place that's real tricky is if I write down like 2, 5. Like, am I talking about a point, right? Am I saying go out 2 and go up 5? 1, 2, 3, 4, 5, whatever. Or am I talking about go to the number line and look at the points between 2 and 5? Which one am I talking about? Right? So there's ways that we can be precise about this. You know, we can distinguish between these, but like generally speaking, there's a little confusion. So you have to know the context in which this is being presented to you to be able to determine which one. All right, so let's keep going. All right,
Cool,
so now.
thank you.
Yep. Baby steps, baby steps. Okay. What's the outside function?
Square root of x is the outside function.
Root x. And then the inside is what's underneath it, right? Take the derivative of each one. So I hope one thing you've taken away from the last few weeks is that when we take the derivative of the square root of x, I've asked you to try and just memorize this, that the derivative of the square root of x is 1 over 2 root x. I mean, I know you can rewrite as x to the half and bring the half and make it negative 1/2. I know that, but this is just the cleaner way of doing it. And then the derivative of this is actually pretty straightforward derivative, right? This is just going to be 2x plus 4x cubed. And now we just apply the formula. Is this making sense to everyone? Like, is there anything tricky about this yet? I mean, I know there's little tricky parts, but have I blown anyone out of the water yet or no?
I think my only question would be is, I know you said we can apply the chain rule as long as we recognize the composition.
Mhm.
I guess my question would be is how do we know that's what we're looking at?
Yeah. Maybe you can do it by thinking about it the other way. Is this just the sum or difference of two things? Is this just something plus something or something minus something? Right? Is this? I mean, it is, right? These are being added together, but do you see it's underneath the root? So technically, it's not just two things separated that you can do each one, right? So it's not a sum, it's not a difference. Is it a product? Do you see something times something here? Okay, no. Is it a quotient? No, right? So really the only thing left is that it's a chain, that it's a composition, that it's something that lives inside of something else. And so we have this, that lives inside of a bigger function, right? And each one of them individually is a simple function. Simple in the sense of they're not, right? Square root function by itself is a pretty simple function. X squared plus x to the fourth is a pretty simple function. It's a polynomials, right? So I don't know if that helps, Isabella, but
No, it definitely does.
it might just take time and just practice to start to get the recognition. All right, here I go. I'm going to evaluate the derivative, but I'm going to replace x with g, right? So it's going to look like this. It's going to be 1 over 2 square root of g, x squared plus x to the fourth, done, times g prime, which is 2x plus 4x cubed. Is that right?
Shouldn't that second be in parentheses?
Has to be in parentheses, the second piece, right? So why does it have to be in parentheses? Because if you don't put parentheses, the only thing you're multiplying are these two, right? That's all you're multiplying, just this times this. It's like if I told you to do this, 4 times 2 plus 3. You're going to do the 4 times 2, right? And then you're going to add 3. That's different than this. That's 4 times the sum of 2 plus 3. So that's 4 times 5. That's totally different. And so when we're saying multiply here times g prime, that means the whole thing, right? Not just one piece of it, the whole thing. So you have to have that parentheses there. And I will take off if you forget it, because it's completely off. It's wrong, right? I'm not going to take off a lot, but I will every time you miss it, I'll take off. Okay. Now we haven't talked about like trying to like clean this up or make it look nicer or anything like that. I don't want to focus on that. I want us to focus on the idea of this right now. The most I could probably do here is move all of this up to the numerator, right? So I could like, because that is a fraction, I could move this up here. And then I could also factor a 2 out, couldn't I? I could pull a 2 out of both of these and then kill off that 2 on the bottom. But I'm not going to. I'm just going to leave it alone. All right. I think y'all are ready for me to turn the screws. Have y'all heard that before? Have I used that before in here? I feel like I have.
No, I've never heard it before.
You've never heard that before?
Nope.
No, am I really? I would say I'm showing my age, but this predates like my existence way beyond.
It's just an old saying.
It's an old saying that has to do with torture. So like they would put people like on the rack and stretch them out, right? And they would turn the screw to stretch them out, and or they put your head in the vise and turn it and squeeze it. Come on, tell us where's the stash, where's the money, or torturing people. And they turn the screws to make it worse and worse until you gave up whatever you need to give up, or if maybe you didn't believe what those people believed, right? They just torture you because you're not like them. Okay, we continue.
Middle ages were a fun time period.
How about this? I'm gonna make this one fun. Let me read this to you. Y equals sine of x times sine x. Did I read that correctly? Sine of x times sine x. So when I said of, that's composition, Isabella. That's when you know you've got composition in there. All right, so this looks a little bit crazy because we have not had this before, right? Everything's been pretty much like two functions. Well, it still is. It still is there's an inner and an outer here. The inner one is the x sine x. Oops, call it G. The inner one is still just the inside of that. Oh, come on. The outer one is the sine x, isn't it?
Yeah. So f of x is sine x and g of x is x sine x.
Yeah, I forgot to put f of x. So if you took this x sine x, and plugged it in right there for x, you would get sine of x sine x. Any questions on that? How about derivatives? What's a derivative of f?
Cosine X.
Cosine X.
Right, that's cosine. Now, the derivative of g.
Isn't that also cosine X?
Sine x plus x cosine x.
Product rule.
Oh, right, product rule.
See it? I tried to sneak it in there on you, right? So we now have to recognize that that g function is just its own thing, right? So we need its derivative. And if its derivative turns out to be a product rule, well, then it turns out to be a product rule, right? So I'm going to run the product rule on this. The product rule says I should take the derivative of the x times the other one, then add to it the derivative of the second one times the first one. That's my product rule applied to this. I have not done the derivatives yet, so I still need to do that. So I'm going to take derivative of x, which is 1. 1 times sine x is sine x. Derivative of sine x is cosine x, but then times x. So I'm going to write it this way, plus x cosine x. Questions? Y prime. All right, so I need to look at the derivative, which is up there, it's cosine, right? I need to replace that x in that derivative with g, which is this. So that's going to look like this. It's going to be cosine. Inside of it will be x sine x. And then I'm done with the first part of the formula, right? That was, I didn't write it down. This is f prime evaluated at g. And then I need to multiply that times g prime. G prime is all that other stuff that we found right here, right? That's g prime. So I need all of that in parentheses being multiplied next to it. So here times sine x plus x cosine x. That's a cool one.
Yeah. I gotta say, the product rule is the one that catches me off guard the most, because I see those multiplication and just want to multiply my derivatives.
Do each one, right?
Yeah,
You
I
see
just, yeah,
cosine,
no, one
right?
times cosine.
One
Sure.
times cosine, right?
Yeah, I keep on doing that.
Yeah. You're not alone, trust me.
Is there is there a way to like distinguish this from the power rule? Like when to use it?
What do you mean the
Kind of
power?
like what Isabella was saying.
The power rule. I'm not sure what you mean.
Well, you know, like on a power rule, you just exponent comes out front, take the derivative of the inside, and then just take the exponent. But this one, there's like when to use which one.
Well, the power rule you're referring to is when you have x by itself to a power, right? X to a power, and then you bring the power out, you subtract 1 from the power, right? That's the power rule. What I think what you're referring to maybe is like here, because we did bring the power out, right? Like right here, we took the derivative. This is the power rule, right? Because we were taking derivative x to the 4th, so the derivative is this. I'm not quite sure I understand the question, so I'm not, my response is not good here.
Sorry, I guess it goes back to the whole like identifying which, like, you know, if I'm using the chain rule on this versus using a power rule kind of thing.
So when you see this, do you see a power? I don't know if you were referring to this problem, but I'm trying.
No, not really this problem, but like the previous two with the exponents. So it's more like,
yeah. Okay, so let's go back to this one right here. Okay, let's just talk about this right here. Are you saying that you want to use the power rule here and not do any of this? Like you want to bring that 4 out and then do what? Something to the 3rd like this?
Yeah, which like I know you're supposed to use the chain rule. It's just like how do you know to use the chain rule in the systems versus like seeing like, oh, I accidentally saw it as a power rule or some shit like that.
Well, the thing is, you can't use the power rule here because this is not just x, right? This is not just an x to the fourth. If it was just x to the fourth, we'd be done, but it's not. So you can't use the power rule, right? I'm trying to figure out like what would tip you off. What would tip you off is the fact that this is not just x to a power. So you can't just do this. And I see, I'm not sure what you would put in here. Like, are you just going to put sine x here and then be done? Or, you know what I'm saying? Yeah, so I don't know. Let's keep cranking. And I mean, like I said, I think it's going to take time and just practice to start to get comfortable with what you're looking at and what you need to do with it, right? I mean, trust me, if there were like if I could just say like, every time you see this, do this, I would tell you that if that's the way it was. But unfortunately, that's not the way it is. Everything is so fluid. Like every problem is uniquely different, right? So there's no like easy thing I can tell you other than here are the rules. Let's see. I wanted to graph this one. I don't know. I was curious to see what it looked like graphed. It was sine of x times sine x. Oops. That was the graph of the original function. We found its derivative to be cosine of x times sine x times, in parentheses, sine x plus x cosine x. That's its derivative. So let's check. Anywhere I see a flat tangent line on the red one, I should see an x-intercept on the blue one. So let's look for some flat tangent lines. I have a flat tangent line here on the red one, and the blue one does have an x-intercept there. Looks like I have a flat tangent line about here, and yes, looks like I have an x-intercept. Oh, I have another flat tangent line here and an x-intercept. Maybe another flat tangent line there, another x-intercept. Flat tangent line here and an x-intercept. It's looking pretty good. It's looking pretty good.
What's that one look like if we zoom out a little?
That one
What's
at
that?
5 looks kind of weird.
You want me to zoom out?
Yeah, what like that one looks like it's gonna do weird. Yep, nope. That one's weird.
That looks pretty cool.
Yeah.
So
We've
could
had
you
a
zoom in
couple
on
that
5?
look weird
Oh,
like
God.
this, but this is the weirdest one, I think. Because it
Yeah.
does like a heartbeat pattern and then gets bigger.
Ethan, did you say something?
No.
Okay.
Sir, I asked if you could zoom in on 5. Or
Oh, I'm
x is equal
sorry.
to 5. That's okay.
Wait, zoom in
I
on
looked
what?
on x is equal to 5 and see where the
Okay.
derivative is right there. That looked kind of weird. I was a straight line, but it goes below and above, or is it
What, the derivative or the original function?
for both? So for the derivative, it goes below and then it goes above the x-axis. However, on the original function, it's just flat. Is
Well,
a
it looks
curve?
flat, but it's not.
Oh, I see.
You see?
Okay, yeah.
Yeah, sorry.
That looks kind of odd.
My view is probably a little different than yours. I can see this little detail a little better. You see how it drops down?
Yeah, I can see that.
So it's like flat here and then it dips down. So your derivative should be negative, then 0 again, then it has to come back up. So derivative should be positive.
Yeah.
And that matches with what's going on right here.
Yeah, there it looks pretty flat to me. So
Yeah. Yeah, it does. Yeah.
it's odd.
From your view. This one's a little more exaggerated.
Yeah, at 2, it's much more obvious what's going on.
I think the further you go out, the flatter it gets. Check that
Oh,
out.
man.
Look, it looks like it's getting flatter and flatter. Look what's happening here. Oh, I wonder what happens as you go out to infinity. These are going to get, this is like asymptotically approaching flat here too.
Mm.
Let's go look at one over here.
Oh, God.
Yeah, that looks almost flat. Yeah, it's still not though. You can tell from the derivative.
Right.
Okay, yeah, all right, let's get back here. Man, technology is so awesome. All right, let's do another one. Here's one that students struggle with a lot. Secant the square root of x. Yeah, students struggle with this one quite a bit. So is everyone comfortable with the idea that this is composition? We have an inner and an outer. Okay, so inside, outside. All right, let's go. I haven't called on y'all in a while, so let's try this. This will be fun. Theodore, you'll be up. What's the inside function?
The inside function is going to be the square root x,
Okay, what about the outside?
secant x.
Okay, good. All right, Daniel Wilson, you're up. You've got the primes.
Let's see. So g of x will be 1 over 2 root x.
Yep. Now,
And
the other one you may not know off the top of your head. It's okay if you don't.
let me look at my sheet right fast.
Okay, there you go. At least you know where to go, right?
The derivative of secant x is secant x tan x, right?
Yes, good. Secant x, tangent x. Okay, good, good. Now, the tricky part to this, we're all okay with the fact that G prime is just gonna be G prime. Like there's nothing you have to worry about there. It's just, that's G prime. The tricky part is that you've got to take the derivative and plug into it G, right? So everywhere you see an X, you have to replace it with root X, right?
You plug it in twice then?
So you're gonna actually plug in twice. It's gonna look weird, but that's what it is. So Deanna, you wanna finish it off? Because you did well on that first part.
All right. So y prime equals secant root x
Yep,
tan root x
yep.
times 1 over 2 root x.
There you go. That's it. That's it.
Oh, that's really cool.
Yeah. So be careful here because this cannot happen, right? That you cannot cancel that root x. That is not okay. This root x is trapped in the tangent. This root x is trapped in the secant, right? So maybe the most you could do here is rewrite it like this: secant root x, tangent root x over 2 root x, like that would be okay. Good, good. What do I see? I see all sorts of things with secant because it appears twice, right? That's the thing that students have issues with. Okay. I'm debating right now, do I keep going with harder problems or do I show you the next approach? I have to show you the next approach. I have to for reasons you'll understand later. But what do y'all want to do? Do y'all want to keep going harder problems or you want to see the next approach?
Let's see the next approach first.
Yeah, I'm seeing a lot of shaking heads yes for that. Okay, so here's the next approach. And I'm going to do every problem we just did with the other approach. All right. So let's go back to the very first one we had, which was this one. I hate giving people both, like 2 different ways of doing it. It's not to confuse you. It really has to do with the fact that sometimes this way is easier. Okay, it makes more sense to people. So let me do this.
It's like the 2 different definitions for the derivative.
Exactly. It's really because there's two people that discovered calculus and they both did this different ways. They both did their chain rules differently. So I'll show you, this is actually the motivation for this second method is that what we just saw was Newton's way. What we're going to see now is Leibniz, the other father of calculus, is his way of doing it. All right. So first thing I want to mention to you is this: y prime. The other notation for this is dy dx. Does that look familiar to you? When I was first telling you, hey, here's a derivative, here are the various notations we have. That means the same thing, right? Dy dx. So the way you say this is we are taking, this means this is taking derivative of y with respect to x. That's the way you would say that. Dy over dx verbally means you're taking the derivative of y with respect to x. So you're figuring out how much does y change if I change x a little bit. It goes back to the idea of the derivative is the slope of the tangent line. So if I'm going to try and find the slope of this tangent line right here, then what I'm asking is for the slope, right? Rise over run, right? M, which is rise over run. And the run is your left and right, right? That's your change in x. And your rise is your change in y. And so basically slope is always change in y over change in x. The key point here is that we take a limit. And when we take a limit, what we do is we let that second point turn into the first point. That's where this turns into dy dx. So this notation just means you're taking the limit of a secant line. Let's not get bogged down with that. Okay, that's just a reminder of what this is all. This all is connected to rise over run. All right, so here's the way Leibniz approached it. Leibniz said, the way that Leibniz wanted to look at this is this. He said, all right, I realize that this is composition. So Leibniz said, I'm going to rewrite this way. Y is equal to sine of, and then he didn't want to put x squared plus 1. He said, I'm going to say it's sine of u. He just called that thing inside something else. And then he said the u that's inside is x squared plus 1. So do you agree with this? If y is supposed to be sine of x squared plus 1, then if I tell you that y is equal to sine of u, and then I tell you that u is x squared plus 1, then this is true, isn't it? If you replace that u with this, then you get that.
Is this kind of like u substitution, college algebra?
You could call this substitution, sure. Yeah, you're substituting this expression, you're substituting this out for u, right? Now, the question is, what do we do now, right? So here's what Leibniz did. Leibniz said, okay, I'm going to look at that equation. And what I'm going to do is I'm going to take the derivative of this with respect to u. So he said, I want to know what is the derivative of this y with respect to u. See, because on the right-hand side of the equation, isn't the variable u? It's not x, right? So we have two variables here, y and u. So he took the derivative of y with respect to u, which should just be cosine of u. I want this out of here. Put that over here. Okay. Do y'all agree with this? The derivative of y with respect to u should be just cosine u. And then he said, all right, now for this one, the variables are u and x. So let's figure out what the derivative of u with respect to x is. And that would just be what?
2x.
2x, right? So we know what dy du is, right? We know what du dx is, yes? Now here's the brilliant part. We want to know what dy dx is, right? We want this. We want dy dx. What Leibniz realized is that if you take dy du and multiply it times du dx, the du's cancel, right? Like this is just, dy dx can be rewritten this way. Y'all see that? It's like these things would go away and yeah, they are equal, aren't they? But see, we're not going to cancel them. because that's exactly what we know. dy du is this, right? And du dx is this. So what we're going to do is just write down this right here, that's dy du, cosine u, times, and then we're going to write down du dx, which is 2x, and we're going to multiply that times 2x. And we're almost there, okay, because all we have to do now is replace that u with what?
X squared plus 1.
What is u? Yeah, u is x squared plus 1, right? So this becomes cosine of x squared plus 1 times 2x, which is exactly the answer we got before. Now, if this confused you, let me do a few more, okay? I mean, you got to see a couple of these to start to catch on. So let me do the next one we had, which was this one. Oh. So Leibniz would have done this. We said, okay, this is a composition. I've got like this inner and outer thing. So it goes, okay, ultimately I have y equals some crap to the 10th power, right? And then the crap that's inside is actually all this stuff right here. And then he would take the derivative of these. The two variables in this first one are y and u. So he would figure out what dy du is. What is dy du?
10u to the 9th.
10u to the 9th. And then figure out what du dx is, which in this case would be the derivative of this, which is just 4x cubed plus 6x. And then to actually answer the question, dy dx, all we're going to do, and this is what happens every time with this method, is you take these two answers and multiply them together, and that's your answer. So I'm going to take 10 u to the 9th times, and then in parentheses, 4x cubed plus 6x. And there's one more step. I have to replace the u with what u is, right? Ten x to the 4th plus 3x squared plus 1 to the 9th and times 4x cubed plus 6x. Same answer as before. Let's do a quick poll. Okay, I'm launching this poll. This is an old poll, so it should say like number 1 blue, number 1 green. Let's just do the first two choices. So the choice that says number 1 blue, that means you like the method I showed you earlier. Number 1 green means you think you like this method. And then the other two means you hate all of this, like you just hate it all. No. So let's see if people like the first or second method more. While you're doing that, I'll get the next problem ready. All right, that's pretty much everyone. So I'll end the poll here. I think you can see the results there. Oh, one person doesn't like it. Oh, I'm sorry. I appreciate the honesty. All right, I think that's overwhelming that the first method looks preferred. Yeah. We're gonna do this poll in a little while again. All right, we'll see if you still keep that perspective or not. Okay, you ready? This one, you do have to realize this is sine x to the 4th. So I'm going to say y is u to the 4th, right? It's something to the 4th power. And then the something I'm talking about is sine x. Then I take the derivatives. dy du is 4u cubed. And du dx is cosine x. And then I just multiply the two together. So dy dx is 4u cubed times cosine x. Last step, replace u with what? What am I replacing?
Sine
u?
x.
Sine x. So this will be sine x cubed cosine x. That matches what we got earlier. So what don't y'all like about this one? I'm just curious. Is it that having to replace the u at the end?
I'm just
So-
more comfortable with the notation f of x and g of x.
Do I-
They
yeah,
don't feel, the actual math doesn't feel any different to me.
Yeah,
Yeah.
I was gonna say I don't really see a difference. It's kind of just like, oh, just replace a letter with this and then ta-da.
Yeah, it is a
It
subtle.
seems
little-
longer, like more work.
It takes longer to write d of y over d of u than it does to write f of x.
Yeah. It's a subjective thing. I mean. All right, so let's see. Well, let's,
Here's the thing that'll affect it for me. What do you think is the better one?
I don't use either one.
I kind of expected that.
Yeah. Because the third method is where you all need to go at some point. You're not there yet, perhaps, but it's the third method is that you're doing it mentally. Okay. So, and I'll show you there's an easy way to do it, but not everyone picks it up. So I have to go through a formal process first. We've got the formal process in place. I'll show you the third method, but let me do one more example. Let's do this one. I'm going to skip one of the ones we did. I want to go right to this one. So if Leibniz was doing this, Leibniz would go, okay, ultimately I've got sine of something, sine of u. And then the u I have is actually x sine x, right? So in the derivative process, dy du, you get your cosine u. And this is the part that Leibniz would have to be careful with, just like you have to be careful, is that when you go to take the derivative here, you have a product rule, right? So that's when you're going to get the sine x plus x cosine x. I'm not showing the work there, okay? It's just understood that that's product rule, yes? Because we've already done it. I will put the little product there so you understand what I did. All right, and then just multiply the two together. If we multiply the two together, we get our answer. So dy dx equals the cosine of u, and then times, in parentheses, sine x plus x cosine x equals cosine. Now I have to replace the u. U is x sine x. That's my u. And I still have in parentheses here sine x plus x cosine x. All right. So I'm going to now give you the third way. All right. The third method. This will be the last one we do. There's another way to look at it, but I think this is sufficient to get you through. Okay. So a little asterisk next to this third method. Okay. A little asterisk here. If this makes you go crazy right now, don't worry about it. Okay. Just stick with the other two methods. You pick which one you like. All right. If you don't like what I'm about to show you. But like I said, this is where you ultimately want to be. When you're in Cal 2, right? You don't want to be doing, you know, writing down what F is and what G is, and then what's F prime and what's G prime, and then using them. You don't want to be doing that. You'll never ever finish the problems, okay? It'll be something you need to get mentally, be able to do mentally. But it's not, you'll get it, okay? It's not impossible, you'll get it. So here's the way it's done. All right, so I see that there's composition here, right? Now, this is really easy to do when I'm in a classroom on a board. Okay, I really can do this a lot better because what I normally do is I write this on the board, okay? And then I say, okay, we have an inner function and an outer function, right? You'll see the inner and outer. I'll actually hold up like usually we have these rags that we clean our boards with. I'll completely cover up the inner function with the rag, like that. Okay, and then what I'll ask you is what is the derivative of sine of a rag? So what is derivative of sine of a rag?
Cosine of a rag?
Cosine of a rag, right? So I'm going to write cosine of a rag, right? So here's my rag. Okay. And then the chain rule says now what you do is multiply that by uncover the inside. Okay, uncover it, take the rag off the thing. We've already taken the derivative. Oops, wrong pen here. We've already taken the derivative of the outer one, right? So now you're going to multiply times the derivative of what's in here. What was underneath the rag? And what's the derivative of that?
2x.
2x. Okay, that's our answer. But I need to uncover that rag, right? Because this rag was right here. I need to uncover it. What's underneath the rag?
X squared plus 1.
X squared plus 1. Okay, that's the chain rule. We'll do another one.
Yeah.
Let's do this one. So we have y equals sine to the 4th x, right? So first thing I'm gonna do is just make sure I understand that it's this, right? So now instead of me holding up a rag, let me do it this way. I'm just gonna cover it with a green, it's gonna be a green blob, okay? That's the inner function. So what is the derivative of a green blob to the 4th power?
4, then whatever's in your blob to the 3rd.
Okay, so if you take a green blob and you raise it to the 4th, take its derivative, you've got the 4 green blobs to the 3rd, yes? Okay, so now what we do, the chain rule says we will ignore the blob there. We've already done the 4 power. Now we move inside and we take the derivative of this, of the blob, right? So what is the derivative of the blob here?
Cosine X.
Cosine x, right? And what was the blob? It was
Sine X.
No. That's the answer. If you can like catch on to this, it makes chain rule like almost seem childish. Okay.
Yeah. Yeah.
But I tell you, in my 20 years of teaching calculus, some students just can't see this, and it's okay. I mean, it's just, I should say, don't see it right away. After they do the chain rule enough, like with the formula, then they start to see like the pattern of it and they get it. And that's okay. But I cannot just teach this way. If you get this way right now, then you don't need the other ways. You're ready to roll. So let me give you one. Let me give you one that we have not done, okay? That's going to be completely different than anything we've done. And I'm going to do it this short way, all right? And let's see if you can follow along. This is really for the people who are following this. I'm going to take sine x, or sine to the 4th, but inside I'm going to put x squared plus 1. I want the derivative, okay? Now, I said I haven't done anything like this. And the reason that it's different is because this is actually a triple composition. This is not 2 functions, this is 3. And you'll see it a little better if I rewrite it like this. Right, that 4th power really means this sine function, whatever's in it, all to the 4th. Do y'all see that? All right, here we go. y prime. Okay, I have an inner function, x squared plus 1. That gets plugged into the sign. All of that gets to the fourth power, right? Triple composition. So what I'm going to do is I'm going to just act like, let me get my my big red one. I have a big red rag. Cover that up, right? Red box, whatever. What is the derivative of a red box to the fourth power?
A red box times 3 to the third.
Times 4.
Times
4 times the red
right?
box
Four-
to the third.
Yeah, 4.
Four,
The third.
4 red boxes to the third, right? That's what I'm going to have.
Yeah.
Times, now, we've done the 4, right? We've done the 4. What's the next layer in?
The next layer in is the sine.
Sine of what?
Sine of x squared to x
But I'm
squared
not going
plus
to
1.
say that. I'm going to say sine of a green oval looking thing, right?
Yeah,
So what is the derivative of sine of a green oval?
it would be
Cosine.
cosine with the green oval.
Cosine of a green oval, right? Cosine of that green oval. Now I've done the now I've done the sine, right?
Yes.
So
and then it'll
I've
be
made my
times
way
2.
into the inside now. And now I need the derivative of that.
Yeah, that's just 2x.
That's just
Mhm.
2x. And then you have to go replace things, right? So you replace the green oval with x squared plus 1. And you replace the red box with what? What's the red box?
Sine
of x squared plus
squared
1.
Sine of
Yeah.
x squared plus 1, but then all of that to the third power. So look, that takes some time. Oh, also I need this in parentheses because that's inside of the cosine. So again, if this is throwing you off, like, don't worry about it right now, okay? Just,
Would you recommend like we use that whole like inner outer way you showed us before?
yeah, let me do this. For this problem, I want to show you the Leibniz way of doing this, okay? Let me show you the Leibniz way. Leibniz would do this. Leibniz would say, okay, look, I've got an outer function. Let me see, let me rewrite it up here. Sine of x squared plus 1 like this, right? All of that to the fourth. Leibniz would say, okay, y is equal to something to the fourth power, right? That's all of this to the fourth. And then Leibniz would say, well, what's inside this u that I have in here is actually sine of some other junk, right? So he would call that maybe w. And then Leibniz would say, well, what's the w? What's the thing inside the sine? Well, the w is x squared plus 1. And then we would do 3 derivatives. dy du is 4u to the third. Then du dw, which would be cosine of w, and then dw dx, which would be 2x. And your answer is these 3 multiplied together. So multiply them all out. 4u cubed times cosine w times 2x. Replace w with what?
X squared plus 1.
X squared plus 1. Replace u with what?
Sine of x squared plus 1.
Replace u, well, I'm going to replace u with sine of w first. And then I'll replace the w with x squared plus 1. That answer is the same as this answer. So I realize this is a lot to ingest, okay? And you definitely will not get good at this until you do a lot of these on your own. Let me see here.
I do have one question.
Yes.
You mentioned that if we're comfortable with doing it mentally, that's where you want us to be at. Would you accept that on a test? Because I know usually you would prefer us to like show our work in pretty good detail.
Yeah, I mean, that is absolutely, I'm okay with you doing it on the test mentally, just so long, you know, if you make a mistake, then you make a mistake, right? Whereas if you use a method and you make a mistake, then maybe I can see your mistake. So it's kind of like, I'm not saying it's all or nothing if you do it mentally, but then it's like, I don't really have anything to check other than what was in your mind, and I'm not sure what was in your mind. So, you know, at your own risk, do that. But if you feel comfortable, that's the way to go. I mean, because it is way more efficient. Let me do a pretty crazy problem just to show you like how this idea works, how quickly you can do a derivative if you understand this. So watch, I'm going to do this. Sine of sine. I did one like this in class last time. Sine of sine of sine of sine of x. Okay, so let me see. I have 1, 2, 3, 4, 5. 2, 3, 4, 5. There we go. So I have a sine function inside of 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 a sine function. And I want to know what the derivative of this is. So the way that I'm going to mentally do this is I see like this big onion, right? These layers of this onion. I have the inner, then the next one out, next one out, next one out, next one out, next one out. So I'm going to start with the outer layer. The outer layer is sine. I know that the derivative of sine is cosine. Cosine of what though? Well, it's cosine of everything that was in here. So everything in here, right, goes here. That means I took everything that was here, right, inside that sine, took everything there, and that's what you see here. It's sitting inside of this cosine. So I've done this. Now I move times, and now I go to the next layer, which is another sine. I take its derivative, I get cosine. Again, but cosine of what? Well, this time it's everything in here. So it's all this. Done. Times, now I go to the next layer. This is just an example of how you're just like working your way through it. This one here, cosine again, but this time I've done that. Now what's in that was sine of sine of sine of x. I would never give you a problem like this, okay? I'm just trying to illustrate how it works. Now I go to the next one, sine again, so cosine, done that one. Sine of sine of x. Okay, move to the next layer, cosine again, done that one. Inside of that goes sine, and then times the final layer, which is derivative of sine, which is cosine. So that's the derivative of that. I'm just kind of working my way through it. All right, we still have some very complicated problems to look at. So
That one right there is kind of brutal.
yeah.
Mostly
No.
keeping track of how many signs you're writing down.
How about this? Y equals, take one kind of a variation of a problem out of the book here. Just so you know, I'm not just like trying to come up with the craziest stuff I can think of. I'm going to do it the fast way first, and then I'm going to do it either the Leibniz way or the Newton way. So for this, what I see is a bunch of stuff to the 7th power, right? All this yellow stuff to the 7th power. So the derivative of this should be 7 times all that stuff to the 6th power. And all that stuff is just x squared over x cubed plus 1. So I've done the 7. Now I have to look in here and take the derivative and multiply it here. But when I look in there, what do I see?
Quotient.
Quotient.
Quotient rule. So I have to actually put the quotient rule right here next to this. So when I do my quotient rule, I'm going to do the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So again, I had all this junk to the 7th. So I said, okay, the derivative of a bunch of junk to the 7th is 7 times the junk to the 6th. Done with the 7, move inside. What's derivative of that? Multiply it here. Derivative, that's a quotient rule. Well, there it is. That's your quotient rule. I'm done. There's no more. I've taken the derivative. Now, of course, you can clean this up and do some stuff, but I'm not going to. This is the raw derivative right here. Yes, you could distribute and, you know, put these together and then combine like terms and all that, whatever. How about this one? Oh, wait, I told you I would do it the other way. So what do y'all want, Leibniz or Newton? Y'all care? Y'all liked Newton more, so I can do the Newton way. Let me see. If I do
this way
Newton,
best.
I think your way is the best.
Yeah, this just seems way
if
nicer.
you get it, if you get it,
Yeah,
if you
no,
get it.
you can also definitely see it stumbling.
That's right.
Yeah, the whole outer
You can
inner
make
thing is so
mistakes.
much more, I don't know.
So the inner function here would be g of x. That would be the quotient that you have in there. And then the outer function would be the f. That would be x to the 7th power. And then you take the derivative, 7x to the 6th. Then you take derivative here. And that derivative would be a quotient rule, right? So 2x, x cubed plus 1 minus 3x squared times x squared all over the bottom squared. Do you see how I'm just like treating the quotient rule like I've been doing it for like 20 years?
I wonder.
Yeah,
Weird.
so I'm not even taking my time on quotient rule anymore because that was last week, right? That was last week. So we wanted, that's why I was saying we have to be comfortable with this quotient product, because if you're still having a lot, now, I'm not saying you're going to do it that fast, but if you have no idea where any of that came from, that's an issue, right? Okay, so now what I do is, well, the G prime we said was easy, right? That's just going to get tacked on. But now I have to evaluate this, replace that X with the G. So if I take this 7, replace that X with this to the 6, that's this. And then I do times this, which is this. Let's do another one. I wanted to give you examples to work, you know, but that's what homework is for. Let's do this. Y equals, let's go x minus 1 to the 4th over, man, x squared plus 2x to the 7th. Why don't I give you a minute to think about this? This is the first problem I've done like this, and man, this problem right here is a type of problem where I hope I can convince you that you want to get to the fast method as soon as possible. Okay, but I want you to just consider it, think about it, and give you about, I don't know, 3 or 4 minutes just to kind of see what you think about it. I'm gonna begin working it. Just in the background here.
Question. Wouldn't that be x squared plus 2x to the 14th power?
Yes,
Okay,
It's
you gotta
the same.
verify I was doing that right.
it will after I do the next step. I just want to make sure I understood it was the bottom square.
Wait, why would it be 14th instead of the 9th power?
Okay, so it would be the 9th power if you were like adding the exponents together, but since you have something that's already raised to an exponent, raised to another exponent, then you multiply it. So think of it as like you're saying x squared plus 2x to the power to the 7th power, and you take whatever number that is, and then you multiply it by itself again. That's gonna be x squared plus 2x to the 14th. So if it was like x squared plus 2x to the 7th times x squared plus 2x to the squared, then you would add them together. But since you're taking the whole thing and squaring it, you multiply the exponents.
You could vision this as you could break that apart into two separate x squared plus 2x to the 7th being multiplied together, which you would then
Yeah.
add those 7s together.
So I used to have this dilemma when I was in your position where I still had questions about these little rules. And I used to just convince myself of it this way. If you take x squared and let's say you cube it, right? The question is, do you add those two numbers or do you multiply them, right? So the way that you can convince yourself is to just do this. Well, what does it mean to cube something? It means to multiply it times itself 3 times, right? But each of those is just x times x, and then another x times x, and then another x times x. So how many x's do you have total? 6, right? So the only way to get to 6 is if you did multiplication, right? As opposed to this, x squared times x cubed. Now you're going to add them. Why? Because this is x squared, x times x, times this is x cubed, x times x times x. And that's 5 x's. So that's x to the 5th. And that means you had to add those two to get 5. I don't know if that helps, but that's the way
Yeah, I got it now.
understood the rule completely. That's the way I would convince myself of it. All right, so let's talk about this one because we're not done, right? I'm not finished with this. I just kind of put it out here. So you have to look at this first and realize this is a quotient rule. Like ultimately, you've got a bunch of crap on top of a bunch of crap, right? So you've got to apply the quotient rule. And so I'm going to follow the quotient rule. The quotient rule says I'm going to take the derivative of the top. So here it is. Here's the top. I need to take its derivative. Then I need to multiply it times the bottom. Then subtract from that the bottom, take its derivative, right? The derivative of the bottom, and then times the top. Here's the top. Then all of that over the bottom squared. Understand? Now, each of these problems, this and this together, those, well, not together, those individually are chain rule problems, aren't they? Because I have composition. I have a function inside of another function. I have a function inside of another function. So you would almost, if you're not comfortable doing those mentally, you would have to do them on the side individually. You'd have to say, okay, I have x minus 1 to the 4th. And let's just, even though I shouldn't use y again, I'm just like, please understand, everything I'm doing in green here is like I'm in a new world, okay? So like this is a new universe I'm in, and I'm just gonna figure out what this answer is. I'm gonna try and take derivative of that. So I'm gonna say, you know, the outer function is f of x, which is x to the 4th. The inner function is the thing inside g of x, which is x minus 1, and then I find the derivatives of each one. Do you all understand what I'm doing here? I mean, I'm doing what we did earlier, but now it's just a smaller piece of a bigger problem, right? So this is x to the 4th, this is x minus 1. The derivative of x minus 1 is 1. The derivative of f is 4x cubed. And then I have to be careful to plug g into that x. So I get 4x minus 1 cubed times 1, which is just 4 times x minus 1 cubed. That's going to be the derivative here. You then have to go do the same thing for this one and go work that out. So I'm not going to do that. I've done one of them. You can do that one on your own. This one, I'm going to get 4 times x minus 1 cubed, then times the bottom function minus, now this derivative here, I'm going to do this one with the fast way. I've got all this junk in here, right? All this junk, which I will cover up with my towel. My towel to the 7th, that's going to be 7 times the towel to the 6th. And what was my towel? I'm going to erase everything. Nope, there we go. My towel was x squared plus 2x times, now I've done the 7, I go in here, take derivative of that, which is 2x plus 2. And I'm done with the derivative at this point. But I still have this times x minus 1 to the 4th. Then all of that over x squared plus 2x to the 14th, because again, what we just talked about, these two multiply. We having fun yet?
That was a cool problem.
Yeah. So on a test, I would accept that as an answer. Okay, that would be okay, just like that. On your next test. But I want to just show you something on this one. I'm pulling out a GCF, greatest common factor. There are two terms up top, this one and this one. They both have an x minus 1 cubed, don't they? This one has an x minus 1 to the 4th. This one has an x minus 1 cubed. So I can pull an x minus 1 cubed out.
Shouldn't you leave that 4 up front?
No, I'm not pulling the 4 out.
Oh, you pulled, that's the part you pulled, right?
Yeah, I'm pulling this part. And then the x squared plus 2x I have to the 7th here, and then x squared plus 2x to the 6th here. So I'm pulling 6 of them out. Okay. What does that leave me with? Well, I pulled this x minus 1 cubed out. I pulled 6 of these out. So I should have the 4 here still. I should have an x squared plus 2x in just one of them. That's all that's left in the first one. Hold on a second. Sounds like there's someone in my house. Oh, it's you. Okay. All right. So I pulled that out. That's all that's left here. Here, I have a minus and then a 7. And then let's see. I pulled 6 of those out, right? So that's all gone. And then I still have this 2x plus 2. And then I pulled 3 of these out. So I still have an x minus 1. And then all over the x squared plus 2x to the 14th. Do you understand? I just pulled the GCF out,
Yeah,
and then 6 of those go away. With 6 of those, that turns into an 8. I can cancel 6 of those.
some of the grodiest parts of the math.
Yeah, and there's more. I can distribute the 4 through. I can expand this out and distribute the -7 through, and I'll have a pretty decent expression. Watch. I'm trying to show you where we're headed, okay? Because we will have to do this algebra later. So now what I'm left with in here in the bracket, I have to distribute the 4 through 4x squared plus 8x. That's this distribution. I'm going to FOIL this one up here. This would have given me 2x squared, and then it would have given me minus 2x, and then plus 2x. Yeah, that's right. And then minus 2. These would have canceled. So I would have just had a 2x squared minus 2 there. And then I've distributed -7 there. So it would have had negative 14x squared plus 14. I know it's making you ill, I can tell. I don't even have to look up. I know. Okay, that's where we are. And I combine these things together and I'll have a pretty decent looking thing. It'll be x minus 1 cubed. I'm not going to use a bracket anymore. Just going to use a parenthesis. I have -8 x squareds. I have an 8x. And I have a plus 14. That's my not so bad looking derivative.
That's actually a pretty nice and clean derivative.
Yeah, it's not
for that-
not as bad as it looked up here, right? Like up here, it looked terrible.
Like the worst part of that there is the 8th power on the bottom.
Mhm. Yeah,
You
these
can
are-
pull a 2 out of that top right one of the numerator.
here. Could I pull
No,
the two?
no. The answer.
Okay.
Oh, could
do
I
have-
pull? Yeah, I could pull 2 out of this.
I do have one question.
I don't know. That's gonna
So,
make a difference.
On the last part, why is it -8x squared instead of -10x squared?
Oh yeah, thank you. This right here. Sorry, I messed that up.
Oh, yeah.
That's a 10. Thank you. 10x squared. I think what I did is I accidentally looked at this, I think, right? No, what did I do? I don't know what I did. No idea what I did. Okay, we've got 8 minutes. And this is where I have to kind of like release you to the, it's like it's time for you, children, to go on your own.
I have one question before we go. Can we see what that one looks like?
Yeah, we can look at it. So look, I know that this is going to be a challenging homework assignment, but it's vital that you go through it and understand it and come get help or go get help from tutoring lab or whatever you need to do, because the success that you have in this class is going to now depend directly on your ability to do this. So put all you can into it. X squared plus 7x. Am I getting that right? No, 2x to the 7. Here's what it looks like. Not that bad.
I wonder what that derivative is going to look like.
Yeah.
It's probably going to be mostly a flat line.
Let me see here. Trying to think of something real quick here. I don't think that Desmos will do a derivative. Hold on.
you can answer. You just need to set the top function equal to f of x, and then the next one f prime of x.
You just put f prime? Okay, I figured there was some easy way to do this. F of x equals this, and then just put f prime of x. That's just sick, man. So it graphed the derivative. It didn't give us what the derivative was, but it did graph its derivative there. Hard to see it, but I do see a flat tangent line here. Right, y'all see that? Which means the derivative should have an x-intercept there, which it looks like it kind of does. Now let's go to some different software. Let's go to Wolfram Alpha. So for this, let's put in the original function, which is y equals x minus 1. What is it, cubed? Sorry, cubed over x squared plus 2x to the 7. Did I get that right?
X minus 1 to the 4th over
Yeah.
x squared plus 2x to the 7th.
So this should give us a graph. And it's just insane. It's insane what you have here. Look at this. Look at this right here. How long did that take? That's the computer's answer for the derivative. All I did was typed in the original function, right? I just typed in the original function. It graphed it. It did an expanded form of it. It did the derivative of it. Found the max and mins. Crazy. So let's see, does our answer match this? If we pull a negative 2
They
out of it,
factored out the 2.
they factored out a negative 2 from here, didn't they? They
Yeah.
pulled out a 2 and put a negative. So if we pull a negative 2 out of ours, we'll get this. And then they did something on this. They pulled out an x. They pulled out an x right here. And then once they pulled out the x, they could apply the 8 to both. And so they got this. Either way, whatever. Okay, so your homework, right? Get as much of this as you can done. Reach out for help. Watch my homework solution videos. Do your best. All right. I'm rooting for you.
Which
You can do
module
it.
is this, 2.5?
This is 2.5. Yeah. And try if you can to have, enjoy it a little bit. I mean, there is that, that feeling that we've talked about in the past where, we all kind of get that same feeling when you do math and you get it right and you get that little reward, that little good positive feeling you get inside, the little butterflies or whatever you get in your stomach, that you're proud of yourself, you got it right. There's a lot of opportunities for that in this section because it's, these are not simple. So try and enjoy yourself, try and enjoy it. It can be fun if you allow it to be. All right, any questions? Next class, we're moving to the next section. I'm sure I'll answer questions in the beginning about chain rule, but we will move to the next section and we immediately need to be okay with chain rule. Okay, so there's not going to be a whole lot of time for us to I'll absorb it over the weekend. You need to have at least a basic understanding of chain rule before we can proceed. Okay, everyone. Have a great
All right.
day.
Thank you, sir.
You're welcome. Have a great day.
Can you hear me?